Good morning, everyone. Just a quick announcement. Our final exam will be in 2 weeks, May 17th, according to the university's final schedule. This exam will be on May 17th. So like it's a Monday. So it's 2 weeks from today. Okay. And you will have 24 hours to access it. And you can access on Blackboard through Grayscope. The content will be after midterm 2. So it will be after chapter 3. It will be magnetostatics, chapter 5, E&M in matter, chapter 4 and 6, and chapter 7, the one that we are discussing right now. So that would be what will be covered on the final exam. It will not be cumulative. Okay. So don't wait until last minute to study. The practice final is already on Blackboard. There isn't a solution yet. I want you to have the opportunity to try to work it out on your own. And I will upload a solution later this week, okay? All right, any questions? Okay, also, by the way, the second semester E&M elective 4150, we have 9 people. I believe that is enough. I think that is pretty safe. I don't think it will be canceled. So just want to let you guys know, okay? All right. Okay, this is our one last chapter, chapter 7. So after this chapter, we will finally have the complete Maxwell equations because we would have included the time dependence. And chapter 7, some of the content you have already learned in 1520. So I'm hoping it will not be coming as too hard because a lot of these could be a review. Okay, so we'll start talking about Ohm's law. Like I said before, all the situation we've been dealing with is static situations. So for electrostatics, is the charges are not moving, right? They're just sitting still. For magnetostatics, we know that the charges has to be moving in order to create a current, right? Current is your charges moving in certain directions. But not just because things are moving is make it dynamics. Or if you have a steady current, meaning that the current is a constant over time, we still consider that as a static situation. We still consider that as a magnetostatics. We don't call it the dynamics. So only when time dependence comes in, then we will have time dependence and we'll have the electrodynamics. Okay. So we'll start building up the dynamic situation by zooming on the current. So we know that the electrons inside the conducting wire, if there's a current, they must be driven by a force, right? So different materials will respond to the force in a different way, right? So let's zoom in on looking at the current, and there is an equation to describe the relationship between how different materials respond to such a force. So we can look at current density J is proportional to sigma times this force, okay? So little f is, we're looking at force per unit charge. Okay, so J is current density. This force is force per unit charge. And the sigma is the conductivity of the material. So the bigger of a sigma, the bigger of a current you will be able to drive, which makes sense, right? The material is a conductor. It will have a big conductivity. And when you drive a current through a conductor, you're going to have a bigger current, right? If you try to drive through a current through an insulator, well, it's an insulator, you have very low conductivity and you will not have any current. So another way to express express conductivity is by writing it as 1 over rho. Rho is resistivity, right? A good conductor will have small resistivity, and a bad conductor, like an insulator, will have a very big resistivity. So F, so we can all write this F as in rho times J if you wanted to inverse the 1 over sigma. F, as I said, is force per unit charge, right? So what are the sources for such a force when we're talking about just the E field and the B field? As we said, the Lorentz force, if you still remember, the Lorentz force is QE. That is the force from the electric field. And it can also, a moving charge inside a magnetic field will feel a force from the B field, right? The QV cross B. So we have talked about this. And you can combine these two together, so that if you're looking at force per unit charge, will be the F over Q, well, just going to be equal to E plus V cross B. So oftentimes when we're talking about the movement inside the conducting wire, if we're looking at a conductor, right, you have some electric field that is driving the charges. Now, if you also happen to have a magnetic field present, you may have also the force from the magnetic field. But oftentimes the V cross B is very small because the velocity of the charges moving inside the wire is very, very slow actually. So the source from E is dominating. So a lot of times we write how to drive a current inside the conducting material, we will write J is equal to sigma E. Okay. And that is what we call Ohm's law. Now you have no Ohm's law from intro physics. It looks a little bit different like this, right? And this is the microscopic Ohm's law. Okay, so current density is proportional to the electric field. And this is not it's called a Ohm's law, but it's not a law of nature. It's really just a empirical observation. By doing experiment, we see that for materials that they obey ohmic material that obey such a relationship. It's not really, it's not like a law, like a laws of conservation or universal gravitation law of that. It's really just empirical observation of the experiment. And it's quite interesting if you think about it. This is talking about, this is a force, right? This would generate a force per unit charge. And if you have a steady force and produce a steady current, in a sense, it's interesting. If you look at this using a classic Newtonian mechanics point of view, you have a steady force, and that gives you a constant acceleration. And if you have a constant acceleration, your velocity would be increasing more and more and more, and continue to increase your velocity. But here, your current is not continue to increase, it's a steady current, right? Is simply, given this electric field, you can expect this amount of current density. So that implies the charges inside the conducting wires. You can see that it's not like you push it, it can go all the way through, it cannot move freely. In fact, there are a lot of collisions going on during the motion, right? These electrons, they will bump into other atoms along the way. And due to that collision, so that overall generate a steady current. It's not a current that increasing on and on. It's not like how our acceleration generates higher and higher velocity. Okay, so that's microscopic Ohm's law. And they are related, J and E are related by the conductivity of a material. So if you're looking at a very big conductivity, and they are very good conductors, For example, sigma for copper is approximately 6 times 10 to the power of 7. And the unit for that is 1 over ohm meter. Ohm meter. Okay. You could also look at the unit by looking at the unit for J divided by the unit for E, right? The unit for J is current over meter squared and divided by the unit for E is force over coulomb. And you can replace amps, the unit for current, using coulomb over time. You do coulomb over time, meter squared divided by Newton over coulomb. You will be able to relate that to 1 over ohm meter. If you're looking at very small conductivity, like insulators. So for example, the conductivity for wood is very, very small, is tiny. So it's very interesting if you think about what is the electric field inside the conducting material. So we know that. What is E inside a conductor? E is zero inside a conductor, yes. So what does this mean? Does it mean that J would always be 0 inside a conductor then? That doesn't sound right.
But that's for stationary, right?
Right. It just means that the current density doesn't necessarily mean, or the fact that it's equal to 0 doesn't mean that the current density is 0. It just implies that it's constant.
So which part of this is, okay, so let me get this right. You're saying this is just for stationary charges. You're saying E is 0 only for stationary charges? Would you say inside a conducting material, when you have a current driving through it, E is no longer 0 inside those materials? Oops. Is E still 0? Let's say I have a copper wire or whatever conducting wire. I hooked it up with a battery. I drive a current through the conductor. Is E inside the wire 0?
I would say no, because your charges are now moving.
You must have an E field from the battery in order to drive the charge in the first place, yes. And what I want to show here by microscopic Ohm's law is because it's conductors, it has a very large conductivity. For example, if you can view that the sigma is almost infinity, very, very large. So even with finite current flow, for example, if you're looking at E is equal to J over sigma, you can still, of course, you can still have a current inside a conductor. This is, you can drive a current through it. Obviously, J should not be 0, right? But even for, but because a conductor is has a very big sigma, for just a finite J, because sigma is very, very large, your E field is still very, very tiny, could be 0. It takes no effort to drive the current in an ideal conductor, very good conductor. Okay, so obviously J would not be 0 inside a conductor. So just cross it out. It's not equal to 0. The microscopic Ohm's law can be related to the Ohm's law that we are familiar with. So if we still remember, something from, let's say this is a resistor, right? And this is the current, and this is resistance R, and the voltage is V. So do you guys still remember the what we learned about Ohm's law? So if you use a voltmeter to measure voltage, and you use an ammeter to measure current. How do they relate it?
V equals IR.
Yes, that is the Ohm's law we're familiar with. That is macroscopic Ohm's law. And I want to show that it is essentially what the microscopic Ohm's law is talking about. They're just using different physical variables. So this one is what we just talked about. And macroscopic is this. Both of those are empirical observations, right? Both of them can be measured by experiment. So let's see if we can relate those two together. We start with J equals sigma E. And J is current I over area A is equal to sigma times E. And E is voltage over length, right? So V is voltage delta V over length L. So if you're looking at inside this resistor, I'm just going to draw the resistor to be a little bit more dramatic. There's a cross section A and a total length of L. And there's a current running through it, and there's also a potential difference across the resistor. So I can replace J by I over A and E by delta V over L. Okay. Now, another thing that we know about the resistance of a material is R is resistivity. You may still remember this, times length times cross section A. Okay. So this is the resistivity. And the longer it is, the bigger the resistor. And the wider it is, the smaller the resistance. Okay. And since I'm looking at sigma, I know sigma is really 1 over rho. So rho is, you continue to derive this, is going to be L over R times A, which means sigma is going to be 1 over rho, that is RA over L. Okay, so I'm going to plug this in. So I get I over A is sigma. Sigma is resistance times area over L, length, times delta V over L. Hold on, I may have flipped something. Okay, yes, this is sigma, this is not rho, this is sigma. Sorry. Okay, because rho is RA over L. So sigma is L over RA. All right, let's fix this. RA over L. Keep writing it the wrong way. Okay. Okay, L cancels, A on the denominator cancels, and we derived delta V is I times A, right? Current times resistance. So you can see that these two are actually telling you the same thing. They're the same. One is taking it from a microscopic point of view, and this one is a macroscopic point of view, right? What you're measuring outside, when you can't really zoom in to see what's going on, is you take a voltmeter, you measure the voltage. You don't necessarily know, zoom in and see, okay, what is the electric field inside? Okay, so that is the Ohm's law I wanted to talk about. Next, I want to say something about the charge conservation. So charge conservation is a fundamental law of nature. It's just like any other conservation laws. For example, let's recall what we talked about conservation of energy. So conservation of energy says inside a system, or inside the entire universe, energy is always conserved, meaning that if you have an initial energy and a final energy of the system, and if there is a change, let's say your energy increased or your energy decreased, that change can always be accounted by some energy into or out of the system. It's not just gone or disappeared. It can be accounted by the energy input or output of the system. And you can change the energy of a system by doing external work, right? That's conservation of energy. the conservation of charge, you can say pretty much follow the same idea. You have some bunch of charges in here, and you cannot create or destroy a charge, right? If you have a change in this, if you draw a bubble saying, I'm going to view the charge within this area, that is my system. If there is a difference in how much charge you're counting, there must be some charges into or out of the system, right? So that simply is charge conservation, very similar to energy conservation. So how do we describe the idea of charge conservation using mathematical equations? How do we write it out?
E initial equals E final.
That is something representing charge Q. Yes, the same idea. If you have, you want to talk about, so, okay, let's say what we wanted to write down. We want to say that if there is a change in the amount of the charge, Q, if there is a change in the Q, that can be accounted by, or that can always equal to the charge input and output. You can count it by charge in or charge out. So you can see that if there's a change, meaning that Q will be changing with respect to time, you probably need something to describe the change, right? The charge input or out of the system. In what case when your charge flowing in and out of the system? When charge starts flowing, what do you get?
You get a current dq dt.
Yeah, you get a current. So here you probably want something that is related to the current that is flowing. So you want to be able to relate dq dt with some kind of equation for J, current is flowing. Okay. So let's see how we can write that. So I'm going to ask you, look at the following statement. Which of these do you think correctly represent the idea we were just talking about? The correct statement for charge conservation. If there is a change, that change can be accounted by the current. So if you need to think about the current flowing out of the system, would that give you a charges inside your volume? Would that be increasing or decreasing? If you have current into the volume, would your charge be increasing or decreasing? Okay. All right, so that I will give you guys some time to think about, and we can have a discussion, and then when we come back, we can vote. Okay, so a little hint that if you're looking at the amount of charge within a volume, you can write it Q using rho d tau. You may not need this right away, but we will eventually wanted to use this when we derive our charge conservation. Okay, so may or may not need this, but I'm going to put it here for now. All right, I'm going to go ahead and open up the breakout rooms, and after we come back, we can. Okay, 1 second. Okay, it looks like we gathered the majority of the voted already. Any last minute vote? Just a few more seconds. Okay, let's take a look. Which one of these will describe the language we just used about charge conservation? Aha. Okay, so let's look at the first one. The first one is J dot into DL. Now we know that when you have volume current density J is flowing through the entire volume. So you'll be flowing through a cross section, right? So we can't dot that into length. It will have to be dotted into an area, right? So like B be correct. Yes, let's look at if the left-hand side and the right-hand side, it's expressed in the same physics quantity. The change of charge per time, charge over time, this is current, right? Yes, and the right-hand side, this is current. And what does the minus sign represent? What do you think the minus sign is? Yeah. What is the meaning of the minus sign? Why there be a minus sign? Direction of the direction, Nicholas says direction, Liam said direction of the surface vector. So can you say more, a little more about that? The surface vector is pointing outward, right? So if we're looking at enclosing this volume, within this volume, we're evaluating the charge here. Okay, so if dA, well, dA is pointing outward, as you said, yes. And if J is also outward, that's saying we have current flowing out of the volume, right? We have a current, we have a positive flux, meaning that the net flux, the net flow out of the volume is positive, going out. Things are going out. So if current is flowing out, which means, okay, this is positive. And what is dq dt? Meaning that the charge inside the volume is increasing or decreasing if charges are leaving. Decreasing, very good. J indicates the flow of your charges going away, then dq must be decreasing. So change over time, you must have a negative value, right? To make them equal, you need a minus sign. So this is very good. This is a correct statement. What is it saying to us is, if you have a change of your charge within the volume, that can be counted by the current flowing out of the system, right? That charge doesn't just disappear into thin air, it actually become current, and those are equal. That's charge conservation. Very good, B is correct. Now let's look at C. C, the left-hand side is the same, the right-hand side is slightly different. So what do you think about, okay, I'm gonna give me more space. J dot into dA is J dot into dA is equal to divergence of J times d tau. Are they equal?
Yeah, because of, well, I was going to say yes because of the divergence theorem, but that's not the divergence theorem.
It is, you're right. This is divergence theorem. It is a divergence theorem. It's saying divergence theorem is saying the surface integral of any vector is equal to the divergence, the volume integral of the divergence of this vector. So this is divergence theorem. So you can write to the right-hand side using a slightly different format. C is also correct. So the answer would be E, because more than one of these is correct. So it's a little bit subtle there. Okay. Now look at D. This one is writing without the integral format. You know that we can strip this equation out of the integral format. But if you want to do it on the right-hand side, you need to do it on the left-hand side as well. So we could easily do that. Simply, we have to give Q as an integral format, rho d tau. Okay, so this is the charge density times the total volume, give you the total charge. Okay, so dq over dt is equal to negative JdA. We have already talked about this is correct statement for charge conservation. And you can plug in Q, right, is the integral of, so this becomes the rho dt integrated over a volume, right, is equal to, this one is, I'm going to use divergence of J d tau. Okay, the reason for that is I want to get rid of the integration sign. If I have a volume integral here, I also want a volume integral there. So instead of using the surface integral format, I'm going to use this format. Okay, so this one you can see, get rid of the integration signs, you get the rho dt is equal to the negative divergence of J. Now this is charge conservation. This is also charge conservation, but in your book, and normally when we say charge conservation, we refer to this particular format, but they're the same, right? You can see that well, one is the differential format, the other is more the integration format. So also a lot of times you can put this on the left-hand side is this plus this equals 0. This is simply charge conservation. Okay, simply saying if you have a change in your charge density in your area, that change can be accounted by the current into or out of the area.
That's the change in density with respect to time, right?
Yes, change in charge density with respect to time, yes.
Okay, thank you.
Okay, very, very good. So let's look at another question. In the interior of a metal in static equilibrium, the charge density rho is what? Okay, so I want to give you a couple of equations that we are going to use to answer this question. That one of them is the charge conservation we have just talked about. Okay. Okay. And I want to let you know that when we're talking about a steady situation, their charge doesn't change over time. There's no charge buildup. When we are looking at the rho dt is 0. Okay, so you may need to use this equation. I also want to write the Ohm's law, the microscopic Ohm's law. Don't forget about that. You may also need to use that. Okay. You may also need to use Gauss's law. Convergence of E is rho over epsilon naught. Okay. All right, so I'm going to go ahead and open up our breakout rooms. For a couple minutes, we can discuss on this question. It's been a couple minutes. Okay, let's run the clock for 10 more seconds. Okay, any last minute vote? All right, let me close it. You can take a look. We are exactly split between choice A and C. Okay, so we all agree that it could be 0. The argument is whether it's always or sometimes 0. It's asking a metal in static equilibrium. Okay, so if it's static equilibrium, there are two conditions, right? The one that you may always think of when we say static equilibrium, you think about the electrostatics, like nothing is moving. That's static equilibrium. So d rho dt, you can say, well, that should be 0, right? There's no change over time. So if d rho dt is 0, we agree, then the divergence of J is 0, right? Because of charge conservation and they're equal. So d rho dt is 0. We get divergence of J is 0. And if the divergence of J is 0, from Ohm's law, we know the divergence of E is also 0, right? Because the divergence of J is sigma times divergence of E if we simply put the divergence on the left-hand side and the right-hand side. Okay, now if that's true, then rho over sigma naught, epsilon naught is divergence of E, which is 0, which is charge density is 0. Okay, is that weird? Or is it
in the sense that in my head I'm thinking, even though it is in static equilibrium, we don't necessarily know if, or do we know if rho is uniformly distributed?
That's a good question. Yes. So we are obviously consider a overall neutral material. We're not talking about some excesses of charge. And also we're talking about the inside. If you're looking at the interior.
Oh, okay. Okay.
Okay. I was thinking if you think it's weird, maybe you may not think it's weird if we're talking about everything is at rest. Okay? I think you're perfectly happy saying everything is at rest. This is 0. But even when things are flowing, if you have a current, one may hesitant to say this is 0 if you have a current flowing inside a wire and we claim the charge density inside a wire is 0. But I want to argue, as long as you're talking about a steady current, rho is also 0 inside. Because if you're talking about a steady current, right, you simply just, this many charges leaving, if you're looking at this cross section or this volume, you have this much charge leaving the area, but it's steady current, which means there's the same amount of charge flowing in. So overall, you are still looking at d rho over dt is 0. Okay, so d rho over dt is 0 simply doesn't mean that things are at rest, not moving. Things can move, like a steady current. Charges are moving, right? They're moving, and that's okay. As they are moving at a steady rate, the change over time is still 0. So we're talking about static situations, electrostatics. We're talking about the independence of time, not necessarily talking about things at rest, not moving. As long as it doesn't change over time, the d rho dt is 0, and you can derive rho is 0 inside a steady current for a wire. Okay, so it's 0 always. So inside of the wire, you can see that, of course, you have protons and electrons. Of course, you have positive and negative charges. But if things are steady, if you look at zooming locally at any local place, right, you still get overall volume density is 0. Okay, so A is always true if you're talking about a static equilibrium state. And you can see you need all of these to combine to answer this question. All right, so we have done a few of these different concepts. Let's do this one together so we can review some of the relationships. We have a copper cylinder, and it's been made into such a shape, A, B, and C, with different width. They're all connected, the ends to a battery, so the current is flowing through the copper. So let's say you connect this to the battery, right? Okay, and you have a current flowing through it. Rank the order from greatest to smallest. First one, we will rank the conductivity. How do we rank the conductivity? Sigma A, sigma B, and sigma C. How do they compare?
I would say sigma C would be greater than sigma B, which is greater than sigma A.
So you're talking about resistance? We're asking conductivity.
No, I'm thinking of current density. I'm sorry.
Copper? They're all made of copper.
Are they the same because they're made out of the same material?
Yes, they are the same conductivity because conductivity is an intrinsic of the material. Yeah. This is as if I asked you about resistivity, you would give me the same answer because they're made of the same material. Okay, very good. The current, I think you answered the current density here. Let's do the current first. What about the current flowing through A and current flowing through B and current flowing through C? How do they compare?
Wouldn't it be the same?
Yeah, all equal. And why is that?
The charge is moving at the same pace all throughout.
Yeah, they're connected in series, right? You have resistance 1, resistance 2, resistance 3. They're connected in series. Current 1 is equal to current 2, current 3, right? You have to have the same current flowing through. This is also, you can view this as charge conservation, right? If your current IA is bigger than IB, then you might wonder, well, where did this current go? It must go somewhere. But they're all flowing throughout, they must be equal. And current density, JA and JB and JC, how do they compare?
Would it be BAC?
BAC, JB is the biggest, larger than A, larger than C. Yes, very good, because J is current over area. The one has the same current, but the one with the smallest area has a bigger density. Very good. So this is correct. Magnitude of the E field. So this one we need to use microscopic Ohm's law. So how do they compare? E would be.
Is it the same as current density, where it would be greater than E of B is greater than E of A, which is greater than E of C?
Yes, that's correct. Very good. One thing that's not here is about the resistance overall. That is rho A, LA over area A. Now that one is hard to compare. We know that rho is the same, area A, B is the smallest, but we don't really know the length. So if we do also know the length, we can compare the resistance of all three, but we don't know that yet. So this is what we can compare. Okay, one more question. All right, so here we have trapezoid shaped resistor. You have a potential difference across two ends, okay? So potential is dropping in the direction of the current flowing, right? So V naught here, V is here. What can we say about the current density J near the side walls of the resistor? So where do you think? How do you draw the J within? So for example, do you draw this direction? Or how do you draw it? A weird direction? Some other possibilities? So this is asking how if J looks like close to the walls of the resistor. Okay. All right. Maybe take a minute and a half. Don't overthink this. A lot of times your intuition might be just correct. Just intuitively think, what do you think this should be? Okay. All right. Any last minute vote before I close this? A few more seconds. Okay, I'm gonna end this. All right, so we're quite split between whether J has to be parallel to the wall or perpendicular to the wall. So if I draw a current flowing perpendicular, must meant this way, right? Current flowing this way. Do you think that's okay, or was that problematic?
The way I looked at it was J is equal to sigma E. we know that this conductor has a current running through it. And if a current is running through it, we know that there's going to be, I don't know, a E field running through this resistor, right? And we know that when an E field runs through a resistor, it travels in the direction from high potential to low potential, which means that E would be pointing to the right, which means J would also be pointing to the right, which is perpendicular to the wall.
Oh, you mean these wall?
Yeah.
No, the side wall.
Are those not the side walls?
Oh, those are the end walls. So
Okay.
right, you're right that two perpendicular to this wall. But what about the sides?
So then they're parallel.
Okay, they're parallel. And if I draw a current going this way, is that problematic? So not overthinking this. It's really just saying you have current density going this way, as you say perpendicular to the side wall, then you have current leaking out. Obviously, you should not have any current leaking out. They cannot be flowing this way. Where would they go next, right? So they can only be parallel to the wall. And what you said about thinking about the E is very good. But in this case, it looks like we have a much more direct argument if we're thinking about the J being parallel to the wall. So you can also argue, well, the E must be parallel to the wall because J is sigma E. Okay, so this next question might be very simple. Let's give you a more regular shaped E field. So a regular shaped resistor, just a square, nothing weird. So in this case, what does E look like inside? Uniform or horizontal, or would you have some non-uniformity like the fringe effects? So I'm going to let you go ahead and vote here. I don't think we need to vote, but we need to discuss. So go ahead and vote on this one. Okay. All right, let's take a look at our vote. Any last minute vote? All right, go ahead and end this. All right, so if you recall, this looks very similar to capacitor, right? For capacitor, I think, yes, indeed, there will be some fringe effects, but you may also answer choice A if we were following the similar thought we had before. Okay, well, J cannot be perpendicular because your current should not be leaking out of your resistor. It should be parallel to the wall, and therefore E must be parallel to the wall as well. So if I say, if it's more uniform and horizontal, right? If I assume E is uniform and horizontal like this, then you can write down a solution for your potential, so that uniform meaning the divergence of E is 0, horizontal meaning that E is perpendicular to the surface vector, to the end surfaces, right? To your end walls. And from that, you can say, well, V, now if V is equal to V naught 1 minus X over A, being here, V naught here is 0, right? And this is to the positive X direction. So if this is a solution describing what's going on in between, right? That gives you an E, which is the gradient of V, and as V naught over A in the X direction. So this one is uniform horizontal E field. So we argue this must be the case. Why this must be? Now, this is very similar to what we talked previously. You might think, okay, can I use the uniqueness theorem? Okay. Well, the uniqueness theorem saying, well, if you can guess a solution, and the solution satisfies the same Laplace equation, and if it satisfies all the boundary conditions, and then it must be the only solution. Well, okay, within the conducting material, within the metal, we said rho is 0, right, for steady current. So we do have Laplace equation, and this solution indeed satisfied Laplace equation. It satisfied boundary conditions because V at X equals 0 is V naught, V at X equals L is 0. So these are the boundary conditions on the boundary are satisfied. Okay, so using the uniqueness theorem, I argue, well, that must be the only solution for V inside the material. Now, if V is like this, then E must be like this, which is uniform and horizontal. So from that argument, I would argue, well, A is correct. It must be uniform and horizontal. But if we recall the actual capacitor, right, remember, so this is a resistor. This is not a capacitor. What is a capacitor? Capacitor is a plate here and a plate there. V naught, and this might be 0. And the in between is like this, just like we derived. But for a capacitor, you have some fringe effects. And here for a resistor, we do not have a fringe effect. It's really indeed parallel here to the boundary and uniform and horizontal. We do not have these fringe effects. So how is that possible? There are some excess of charges at the surface of the capacitor. There might be some excess amount of charges that on the surface help to shape your electric field this way, so it does not look the same as a capacitor, so not like a capacitor. And in real circuits, there are excess amount of charges built up on the surface of a resistor, okay? So those are actually true. We don't need to use that argument to say why it has to be uniform and horizontal, because we had just answered that using Ohm's law, using uniqueness theorem. But we can explain as a sort of a conclusion step further that it looks a little bit different from a capacitor because we do have some built-up charges on the surface of the resistor to help shaping the electric field to be this way. Okay, so the answer is A. Okay. All right, so next I want to talk about complete circuits. So far we have been looking at just a section of what's going on, but what if we have all the different electric elements connected together, right? Have a complete circuit. So they have various elements. They have conductors, they have resistors. You may have conducting wires, you may have resistors, and you have batteries, and so on and so on. They form a complete circuit. If the current is flowing around, it must be driven, right? So a measure of this is called the EMF. Historically, it has this name of EMF, which is called electromotive force. So it's a historical name. So the idea is if there's a current, current must be driven. So we say maybe this is a electromotive force, EMF. Okay. Current is driven. So EMF is using epsilon to represent it. It's EMF. And we describe using the line integral of the force per unit charge. This little f you have already seen. That is the force, whatever the force is driving the current, it's that force per unit charge. And we call that the electromotive force. Okay, so this force can be any kind of sources. You may be driven by an electric field. You may be driving by a magnetic field, or more complicated inside a battery, you have some chemical reaction going on. You have chemistry, you have quantum mechanics, make it harder to actually visualize what's going on, but those can be possible sources for what's driving the current. Now, I would say the historical name, EMF, is a very bad name. This is not a good name because it doesn't really tell us the physical meaning of this quantity, right? If the EMF, electromotive force, you might be thinking, well, that is a force, so it must have the units of newtons, right? But it's not newtons, and we can say that. So what is a unit for such a electromotive force, which is described to be the total force per unit charge around the closed loop, right? This is force per unit charge around the line integral of that around loop. So what is the units of EMF? We know the units, we will be able to figure out what physical quantity it represents. Okay, I'm gonna go ahead and let you vote. Okay, 10 more seconds, and then let's look at this together. Okay, any last minute vote? All right, let's take a look. The units for EMF, very good. Yes, it is voltage. Excellent. So if you look at this expression, force per unit charge, right? For force per coulomb, that's little f times the L, so that's meter. So Newton times meter gives you, that's the unit for work, right? You can use joules to represent it as well. So joule per coulomb, right? This is energy over coulomb. So if you recall, U is Q delta V, right? This is energy, joules, this is coulomb. So delta V is joule over coulomb, which is voltage. So yes, EMF is actually describing voltage, has a unit for voltage, for potential, electric potential. So even though it's called the force, it's really a electric potential for the physical quantity. And you can see that the EMF, if you're looking at purely the electric field, we know that the line integral for electric field is, so if we use Stokes' theorem, is equal to the curl of E dot into dA, right? The curl of E is 0 for static E field, electrostatics, okay? Now, even if you have current moving, we're still talking about the 0 curl for the E field. So that the line integral for E dot dL is still 0. It's always 0. So you can see that, well, the electric force alone is not going to be able to drive your current all the way around the loop. So to drive the current, you need some other forces. You may have a battery force, which will give you a sort of chemical source. You can have mechanical, like the Van de Graaff generator, right? Mechanical way to drive a current, or you can have a generator to drive a current where you have a magnetic source, but not the static E field alone, not electrostatics alone, okay? Okay, so let's pause here for now, for today, and we will continue with our rest of the discussion on Wednesday. Again, just wanted to remind you, our final exam is scheduled, I'm sorry, 17th. Let's say Wednesday, Monday the 17th. The time doesn't matter, so we will have a 3-hour duration on Monday. I'm sorry, these are not updated. So content will be after midterm 2. All right, make sure that you work out your practice exam as soon as possible. Hopefully you can do it this week. So if you have questions about the practice exam, you can still ask the next week before our actual exam day. All right. Okay, so that's all for today. I will see you guys on Wednesday. Bye, everyone.
Thank you, Dr. Ryan.
Thank you. Bye-bye.